Okay, so today we will spend most of our time talking about physical properties of alkenes, interesting alkenes, and then we'll start talking about addition reactions of alkenes, with the hydrohalogenation reaction being the one that we'll focus on. Before we do that, we have one more item of nomenclature to discuss. Sometimes we can have an alkene as part of a substituent. And this usually occurs when the alkene is attached to a ring. And if an alkene is attached to a chain, you're going to reroute the chain through the alkene because of its priority. So this typically occurs when you have an alkene attached to a ring that has more carbons in it. And so if we have a situation where one of the carbons is part of the ring and the other carbon is outside of the ring, we can call that a methylene group. And we've already seen CH2 referred to as methylene, so this is language we're familiar with. If both carbons of the alkene are outside the ring, that's known as a vinyl group. That's also a term we've used. We've talked about vinyl halides before. And then if we have the two carbons of the alkene and an sp3 carbon attached to the ring, that's known as an allyl group, and we've also mentioned that. We talked about allyl halides back in chapter 7 as well. So this slide right here just shows you how you would use these terms. Methylene cyclohexane, 1-vinyl cyclohexene, for example. Allyl would be used the same way. If you had an sp3 carbon here in between these alkenes, that would be 1-allyl cyclohexene. Are there any questions on the use of these terms, methylene, vinyl, and allyl? Okay. Let's talk briefly about physical properties of alkenes. So they're quite similar to alkanes in that they are nonpolar, they're not soluble in water, they have low boiling points. But there is one difference, one key difference between alkenes and alkanes. And that's derived from the fact that sp2 carbons are slightly more electronegative than sp3 carbons. And so the sigma bond between an sp2 carbon and an sp3 carbon is slightly polarized towards the sp2 carbon. We talked about this in chapter 8 when we were talking about more substituted alkenes being more stable, about how alkyl groups can donate electrons to those sp2 hybridized carbons. That higher percent S character means they attract electrons more strongly. So what that means is that if we have a cis alkene and a trans alkene, here in our cis alkene, we're going to have these weak but measurable dipoles going towards our sp2 carbons. We have the same thing here with our trans alkene. Okay. We see that in the trans alkene, those dipoles are going to cancel each other out. But then we see with the cis alkene, those dipoles are going to reinforce each other. Okay. So there's actually a slight difference in boiling point between these two compounds. Which one would have the higher boiling point, the cis or the trans? The cis, exactly. You have a small dipole here. The boiling point of cis 2-butene is 4 degrees Celsius. The boiling point of trans 2-butene is 1 degree Celsius. So it's a small difference, but it's a measurable difference, and it's attributed to this very small dipole moment that we have in a cis alkene that we do not have in the trans alkene. Any questions? Okay, let's talk about interesting alkenes in nature and industry. Ethylene, our simplest alkene, even though it's simple and has a very simple structure, is arguably the most important alkene in the world because it is the most largely produced chemical in the chemical industry. right? More tons of ethylene are produced and used than any other molecule. And that's because ethylene is the precursor to a whole bunch of different polymers. And we see some of them here: polystyrene, polyvinyl acetate, polyethylene, polyvinyl chloride. All of those originate from ethylene. And you might wonder where ethylene originates. It can be produced in the cracking process of crude oil. That's done in oil refineries, right? You can produce ethylene, and you can separate it out from the other components of crude oil. You can also use it to make ethanol and ethylene oxide, which goes to ethylene glycol. Of course, we're trying to get ethanol from renewable sources as opposed to from fossil fuels. Okay, so ethylene, a very important alkene. In addition to coming from crude oil, ethylene is also a plant hormone. So plants will release ethylene, and what that does is stimulate ripening of the fruit. And then we see other alkenes. One we'll focus on is a retinol or vitamin A. This is a polyene where we have many, many double bonds in the molecule. And at the beginning of next semester, we will learn how retinol is involved in the chemistry of vision. It's essential for us to see. Of course, vitamin A comes from carrots, and so there is truth to the statement that carrots will help your vision. Okay, but lots of different alkenes in nature as well as synthetically produced. So some other alkenes that occur naturally are triacylglycerols. These are compounds that if you studied biochemistry or maybe in a biology class, you've learned about triacylglycerols. So triacylglycerols are esters. This functional group here is an ester. And if we didn't have these esters, if we just had OH groups here, that triol would be referred to as glycerol. So a triacylglycerol is a triester of the triol of glycerol. Okay, and these are lipids. Lipids are biomolecules that are insoluble in water. Triacylglycerols are insoluble in water because they have very, very long carbon chains. These R groups are going to be anywhere from 11 to 19 carbons in length. And so we can cleave triacylglycerols, and we end up with carboxylic acids. This is chemistry we're going to study in 352M. But these species are known as fatty acids. Okay. The R has 11 to 19 carbons, so when you count this carbonyl carbon, you've got 12 to 20 carbons, very, very long chain fatty acids. Why we're talking about them here in the alkenes chapter is these fatty acids are divided into two categories. We have saturated fatty acids, where all the carbons in that chain are sp3 carbons. And then we have unsaturated fatty acids, where we have one or more alkene in that chain. Okay, we know that alkenes are unsaturated. We talked about degrees of unsaturation a little bit on Monday. So that's the difference between saturated and unsaturated fatty acids. So we have here a table showing you the names and structures of some fatty acids, some common fatty acids that exist in nature. And two things you can see from this table. One is you see that all the double bonds in the unsaturated fatty acids are cis or Z using our new E and Z nomenclature. Okay? And we also see that with each additional double bond, the melting point decreases. Okay? So our saturated fatty acid has a higher melting point than our unsaturated fatty acid. And the melting point of the unsaturated fatty acids goes down with increasing numbers of double bonds. We see here that the saturated fatty acid is going to be a solid at room temperature. And so we also refer to those as fats. So fatty acids that are solids at room temperature are called fats. And then the ones that are liquids at room temperature are kind of an oily liquid, so we refer to those as oils. Okay? So why does the melting point go down as we add cis double bonds to these chains? Any ideas? Okay, Claire?
The molecules can't stack as well, and so it makes it so that they don't like pack very well, and so it's easier to break any sort of intermolecular forces within it.
Okay, excellent explanation. So what types of intermolecular forces would that be impacting? Yeah, it's going to be the van der Waals forces primarily with those long non-polar chains. So we see that if we have an unsaturated, or if we have a saturated fatty acid, we're going to have this staggered conformation, this low energy staggered conformation with an extended chain. And we're going to be able to pack two or more of these molecules fairly close together, having stronger van der Waals forces, and therefore more energy is required to break those up and melt the compound. In contrast, when we have the cis alkenes automatically introduce a kink in the chain and make it harder for these molecules to pack together. Question? I suspect that the transalkenes would be comparable to the saturated fatty acids. I'm not 100% sure. I know I just told you that cis alkenes have higher boiling points than trans, but these chains are so long that those van der Waals forces would probably overwhelm the small difference due to the dipole here. But in nature, they exist only with the cis. Okay? You've probably heard of trans fatty acids. We'll talk a little bit more about them later in the semester. Those are unnatural compounds that are synthesized by a process we'll mention later. So you can see the difference even better with these ball and stick models where we see stearic acid, extended staggered conformation, and then each of these unsaturated fatty acids, we have kinks. We have the chain increasingly kinked. This has one double bond, this has two double bonds, and this has three double bonds. And so with the increasing kinks in the chains, it's more difficult to pack these molecules together. You have less van der Waals forces and therefore a lower melting point. Okay, question? There probably is. I don't know that reason. I suspect it has to do with this difference in physical properties. I suspect that in nature, if you need a fatty acid that's a solid, then you're going to make a saturated fatty acid. If you need a fatty acid that's going to be a liquid, then you would make an unsaturated fatty acid with a cis double bond. That's my assumption. Another reason, which we'll discuss in chapter 12, is that trans fatty acids are harmful for your health. They're associated with elevated levels of bad cholesterol and problems with the heart. So a couple different reasons why we see them as the cis alkenes in nature. Okay, but we can explain. We're able to explain why the cis alkenes have, why they're oils at room temperature, why they have lower melting points than the saturated fatty acids. So our fats usually come from animals. Animals will biosynthesize saturated fatty acids generally, whereas plants will make the oils. So plant materials are going to be high in oils. Animals will be high in fats. So there's a special type of fatty acids called omega-3 fatty acids. How many of you have heard of omega-3 fatty acids? Hopefully most of you. Good. Okay. Here are some omega-3 fatty acids. They're unsaturated, so they're oils. The name comes from the fact that omega is the last letter of the Greek alphabet. So if you go to the last carbon of the chain, so the chain would start where our carboxylic acid is, we go to the end of the chain and we count 1, 2, 3, and we encounter a double bond. So if you have a double bond, 3 carbons from the end of the chain, that is an omega-3 fatty acid. Okay? And omega-3 fatty acids are associated with a healthy heart. What types of food is a good source of omega-3 fatty acids? Fish. Yeah, it's associated with fish. There was a time when doctors were recommending consumption of fish oil supplements as a way of getting enough omega-3 fatty acids in your diet. They've changed that recommendation recently, but omega-3 fatty acids are believed to have healthy benefits on our health, specifically on our hearts. But you said they come from fish, and I told you that unsaturated fatty acids come from plants. So the fish are not biosynthesizing these omega-3 fatty acids, they're eating them, they're getting them in their diet. So algae are actually a natural source of omega-3 fatty acids. Okay? I think most people would rather eat fish than algae, so we get them in our diet through fish. Unfortunately, fish are becoming more and more scarce with overfishing going on, and so there's a research to try to genetically engineer other types of plants that produce omega-3 fatty acids so that they would produce higher levels of omega-3 fatty acids. Plants such as soybean or canola in the oils, soybean oils, canola oils. If you can genetically engineer those materials, you could produce higher levels of omega-3 fatty acids, and you could get them from a more sustainable source than the fish. Okay? All right, so let's talk briefly about how alkenes are synthesized. We've learned some reactions for preparing alkenes earlier in the class. So if we were to start from an alkyl halide to try to make an alkene, what reaction would we use? Okay, it would be an elimination reaction. Good. We could call it a dehydrohalogenation. It's a specific type of elimination. And what reagent would we use to react our alkyl halide with? Okay, we'd use a strong base. There are a few choices. I think I heard DBU. That's one that would work. DBN would work. Tert butoxide would be a good one. Okay. Depending on the type of alkyl halide, we might be able to use smaller bases than tert butoxide. Okay, but these are 3 that would reliably allow us to convert an alkyl halide into an alkene. Okay, question? Dehydrohalogenation is a type of elimination. So it's a subset of elimination reactions. This just involves eliminations where what you're eliminating is a hydrogen and a halide. Okay? Yes? Yes. Yeah. Yeah, so these would be the bases that would work the best. Those would work with any alkyl halide unless it was a methyl halide or one that didn't have beta hydrogens. But these would work with any alkyl halide capable of generating an alkene. Okay, can we make alkenes from compounds other than alkyl halides? What else could we use? Alcohols, okay. So what kind of reaction would we use to convert an alcohol to an alkene? Okay, it's also an elimination reaction, and it's called a dehydration, correct? Okay. What reagents would we use? Okay, any strong acid? Okay, sulfuric acid. So we can use sulfuric acid or toluene sulfonic acid. Good. Okay. And so those reactions, those dehydrations with acid, those are going to proceed by either E1 or E2 mechanisms, depending on the type of alkyl halide you have, or sorry, the type of alcohol you have. And so there's the possibility of rearrangements. Do we have another way of performing dehydrations that doesn't involve acid? Okay, phosphorus oxychloride, very good. POCl3 along with pyridine as a weak base. And so that's only E2. So that will not involve carbocations, will not involve rearrangements. So these are the ways we can make alkenes. They're all eliminations. We'll actually learn other ways of making alkenes later in the class. In 352, we'll learn ways to do it that don't involve eliminations. But for now, if you needed to make an alkene, you would have one of these two starting materials, and you would use one of these two reactions. Okay? All right, so let's talk about what we can do with alkenes once we have synthesized them. So the reactions of alkenes are called addition reactions. Okay? So in an addition reaction, we're going to take an alkene. We're going to react that alkene with a reagent that we'll call XY. And we're going to add the elements of X and Y across the double bond, meaning that we're going to break the double bond. And X is going to attach to one carbon, and Y is going to attach to the other carbon. So we'll get a product looking like this. Okay? So in this reaction, we're breaking a pi bond, and we're breaking the sigma bond between X and Y. And in their place, we're forming two new sigma bonds. So these addition reactions are going to be thermodynamically favored. They're going to be exothermic because the bonds that are formed will be stronger than the bonds that are broken. We have here an electrostatic potential map of ethylene, our simplest alkene. And what we see is that the pi bond creates an electron-rich region in the molecule. Those pi electrons are held more loosely than the sigma electrons. They're more available, they're more reactive. And so we have high electron density in the region of the pi bond, which is going to be above the plane and below the plane of that alkene. So they've tilted this model a little bit on its side. So you can see the red patch that's above the plane, and there's going to be another red patch that you can't see in this diagram below the plane. So what this figure tells us is that the alkene is going to be the nucleophile in these addition reactions. Those pi electrons are going to function as the nucleophile, and the XY species is going to function as the electrophile. So the pi electrons from our alkene are going to attack our electrophile. That's how these addition reactions are going to be initiated. Okay. After that, various things can happen, but that's how it's going to start out. Okay. So there's going to be some stereochemistry associated with additions. So I'm going to draw a generic alkene. These four groups can be anything: hydrogens, alkyl groups, functional groups. But with the wedges and dashes, what I've done is drawn the alkene perpendicular to the board. Okay, so it's perpendicular to the board. And so when we react X and Y, when we add X and Y across the double bond, one of two things can happen. The X and the Y can add to the same face, either the top face or the bottom face of the alkene, but you can have both of them on the same face. I'm going to go ahead and draw them both coming from the top face, in which case your product would look like this. Okay. And if these generic groups that I'm drawing with these wedges and dashes were different from each other, then there would be a difference in these two possible outcomes. But when X and Y come from the same face of the alkene, we refer to that as syn addition. And then the other possibility is when X and Y come from opposite faces. One comes from the top, the other comes from the bottom. We'll go ahead and draw X on the top and Y on the bottom. Then we're going to get something looking like this. Okay? Yes?
How would that work? Because you have two different molecules of XY, and then one comes from the bottom and one comes from
You would presumably have a stepwise process to do this type. This one could happen in a single step or possibly a stepwise, depending. But this one, you couldn't do it at the same time. You'd have to have a stepwise process. But this is referred to as anti-addition. Okay? And we'll see the mode of addition is going to depend on the mechanism of addition. There's 3 different addition mechanisms we're going to learn in this chapter. And so some of those mechanisms will involve syn addition. Some will involve anti-addition. Okay? And then another issue that we have to think about with addition reactions is what we'll call regiochemistry. We learned about regioselectivity earlier in the class when we have 2 possible isomers, 2 possible constitutional isomers that can form, and one is major, then that's referred to as a regioselective reaction. So regiochemistry refers to situations where you can produce more than one constitutional isomer. And that can happen in addition reactions if your alkene is not symmetrical, meaning if the 2 carbons of your alkene are not equivalent to each other, and X and Y are different, then you would get a different constitutional isomer depending on where X went and where Y went. So in the individual reactions, we'll have to consider the regiochemistry, namely which of those 2 possible constitutional isomers is formed. So as we study additions, we're going to focus on the type of stereochemistry, and we're also going to focus on regiochemistry, which constitutional isomer is formed. So we have a very helpful table here that shows all 5 reactions we're going to learn in this chapter. They're all additions. The book has shown them with a simple symmetrical alkene, cyclohexene, so regiochemistry is not an issue in this reaction because it's both carbons of our alkene are identical with each other. And the book has not drawn the stereochemistry for you. I think they didn't want to spoil it for you. We'll figure out the stereochemistry as we go and learn these reactions. And so these are named based on the groups that are being added across the double bond: hydrohalogenation, hydration, halogenation, halohydrin formation. Hydroboration oxidation gives you the same result as hydration with cyclohexene, but we'll see that it's actually different in terms of the stereo and regiochemistry. Okay? So these are our 5 reactions that we are going to learn. And the one we're going to start with, we're going to just start at the top and go down. The one we're going to start with is the hydrohalogenation. So here we are reacting our alkene with our HX acids, and we're adding the hydrogen to one carbon of our alkene and the halide to the other. We can look at this table here, which shows the bond dissociation energies for the bonds that are formed and the bonds that are broken in a simple hydrohalogenation. And as we would expect, the bonds that are formed are stronger than the bonds that are broken, 2 sigma bonds versus a pi and a sigma. And so hydrohalogenation is indeed an exothermic process. Okay, so we're going to look at the mechanism of this reaction. But before we do, let's discuss some relative rate data, and then we'll make sure that our mechanism that we propose is consistent with those relative rates. Okay, so HF is going to be unreactive in a hydrohalogenation. All right, so we'll put two less than signs here, indicating that the rate is going to be so slow, we're not going to see that reaction. And then what we see is that the rate will increase as the acidity of the HX molecule increases. So HI is going to react the fastest, HCl would react the slowest. So this suggests that our HX species is functioning as an acid in the rate determining step of the reaction. Okay, so let's draw a mechanism that's consistent with that information. Let's just use a simple symmetrical alkene in this case, cis-2-butene. We'll react it with HBr. So by now you're used to acids protonating the oxygen atoms of either alcohols or ethers. Those oxygen atoms are Lewis basic. They've got lone pairs. We also learned back in chapter 2 that pi bonds can function as Lewis bases. And so we're able to protonate the electrons of a pi bond similarly to how we would protonate the electrons, the lone pairs on an oxygen. So what happens is our pi electrons attack our acid. We protonate those electrons. We're going to cleave the sigma bond between the hydrogen and the bromine. So what will happen as we protonate the pi bond is we're now going to end up with a sigma bond between this hydrogen and one of the two carbons that was involved in the alkene. And what's going to be left behind on the other carbon? A positive charge. So we're forming a carbocation. So this is another way of forming a carbocation. In this case, because I chose a symmetrical alkene, it doesn't matter which of the two carbons I put that positive charge on. Okay? So we're forming a carbocation. This is a new way of forming one that we haven't seen before, protonation of an alkene. And then we're going to generate a halide in the process. I've broken every piece of chalk they gave me today. All right. And we know what happens. We've seen before what happens when we have a carbocation and a halide ion. What's going to happen? Yeah, the halide will just act as a nucleophile and attack our carbocation. And that will give us our alkyl halide. So this mechanism is consistent with our rate data. Which of these two steps is going to be our rate determining step? Step 1. We know that forming carbocations is slow. So we know that's going to be our rate determining step. And so our HX species is acting as an acid in the rate determining step, so it stands to reason that the stronger acid would react faster. Now this method of forming a carbocation is it's different. Before, we would form a carbocation just by breaking a bond. Right? Here we're actually forming a bond, but we're breaking two bonds. And so we're still doing more bond making, which would cause this to be endothermic. And then this second step here is going to be quite fast. Question?
In this example, it doesn't matter, but do you have times when this leads to racemization?
We will, yes, and we'll get to that probably in about 5 minutes. We will address that issue. But yes, definitely stereochemistry. We have a carbocation intermediate, which is achiral, as you noted. So here's an energy diagram for this reaction. We see two transition states indicative of our two steps in the process. We see that the first step has a higher energy of activation than the second step, what we would expect. And then we have the transition states drawn over here with the partial bonds and the partial charges. Let's look at the transition state for step 1. Is that transition state going to look more like the starting materials, or the intermediates? Think about Hammond's postulate. Which one will it resemble more strongly? The intermediates, the species to which it's closer in energy. So these partial charges on the bromine and the carbon, are they going to be closer to 0 or closer to 1? They're going to be closer to 1. So we're going to have most of a carbocation formed at that point, most of a halide ion formed at that point, but not completely. Transition state number 2, is that going to be closer to the products or the intermediates? That'll be closer to the intermediates because it's an exothermic step. And so here indeed, we're also going to have mostly a carbocation and mostly a halide ion, and those charges are going to be closer to 1 than they are to 0. Okay? Question? So you're talking about why is this transition state higher in energy than the intermediates? Yeah, that's a good question. It probably has to do with the fact that you have to have a specific orientation in order to form that sigma bond. And so it probably costs us energy to get the molecules in that proper orientation. That's my best explanation for that. Okay, but very good question. It's not going to be much higher in energy though, but there's a little bit of an energy cost to bring those two species together in the correct orientation. Okay, so let's address not your question first. We've got another issue we're going to get to before that. Let's say that we have a terminal alkene in this case. We're going to react that with HX. Because this alkene is not symmetrical, now we have two different constitutional isomers that we could generate. We could get the halide on carbon 2. We could have a more substituted halide. Or we could get a less substituted halide, having that halide on carbon 1 of our alkene. Okay, so two different constitutional isomers can form based on what you know about the mechanism of hydrohalogenation. Will there be a major product? And if so, which one? Yes, please. Yes, this one right here. Okay, so the more substituted alkyl halide is going to be our major product. Why? Yes, go ahead.
Because then the carbocation intermediate is going to be on the more substituted carbon.
Okay, yeah, this would be derived from the more substituted carbocation. The halide attacks the positively charged carbon, so the more substituted alkyl halide is going to come from the more substituted carbocation. Very good. So this phenomenon was first noticed by a Russian chemist named Vladimir Markovnikov back around 1870. Markovnikov was a colleague of Zaitsev. They actually worked at the same university. Zaitsev was studying elimination reactions, and Markovnikov was studying addition reactions. And Markovnikov noticed in these reactions that when you are adding HX to an unsymmetrical alkene, the hydrogen atom bonds to the less substituted carbon. And so this observation was termed Markovnikov's rule. You could say the halide bonds to the more substituted carbon. For some reason, it's always formulated in this fashion in every book that I've read. But it just means that we get the more substituted alkyl halide from a hydrohalogenation. So this observation is known as Markovnikov's rule. And Markovnikov's rule was an empirical observation when he made it back in 1870. because he had no idea, and neither did any other organic chemist have any idea of the mechanism of this reaction. So the reason was not understood. But now we understand the reason, and we mentioned it, that in the first step of the hydrohalogenation of our terminal alkene, we're going to protonate the alkene, generating a carbocation. We can have the proton attached to the end of the chain. That would give us a secondary carbocation. Or we could have the proton attach to carbon 2, and that would give us a primary carbocation. And we know primary carbocation, high in energy, we're not going to form that. Secondary carbocation, also high in energy, but not as high. So that's going to be our more stable carbocation. Okay. So why is we know that this carbocation is more stable than that one. Why is the more stable carbocation formed faster? Yes, please. Okay, so Hammond's postulate tells us that in an endothermic reaction, the transition state more closely resembles the products. And so the transition state leading to the more stable product will be lower in energy. And therefore, you have a lower energy of activation, and it is formed faster. Very good. So we have an energy diagram showing us that. So here's the reaction with propene, a very simple alkene. So we have one set of reactants here and two possible pathways leading from those reactants. One gives a very high energy, less stable primary carbocation. The other gives also high, but not as high in energy, more stable secondary carbocation. And we know that these transition states more closely resemble the carbocations than they resemble the starting materials. So we're going to have mostly carbocations at those transition states. We'll have partial positive charges that are closer to 1 than to 0. And so that partial positive charge is going to be more stable on the more substituted carbon, meaning that our blue pathway, our blue transition state, is going to be lower in energy than our red pathway. Okay, so Hammond's postulate explains to us why the more substituted carbocation is formed faster. Okay. All right, so we have a carbocation intermediate. So what do we need to look out for in this reaction? We can have rearrangements. Anytime we form a carbocation, we can have a rearrangement. So if we take this alkene, react it with HCl, we would expect to get the more substituted alkyl halide. But that's not actually the main product. The main product has the chlorine on a carbon that wasn't even part of the alkene. And so that has to be generated from a rearrangement. In this case, the ratio between these products was 2:3, and the rearranged product was the major product. So what's happening? We protonate the alkene, generating our secondary carbocation. But whenever we generate a carbocation, especially a secondary carbocation, we need to look at the adjacent carbons and see if there's a group that we could shift to give a more stable carbocation. And in this case, we can perform a hydride shift, shifting the hydrogen over. That gives us a tertiary carbocation. And then our halide, our chloride, can attack that, giving us our major product. Okay, so we get both products, the unrearranged and the rearranged product, but the rearranged one is the major product. Any questions? Claire?
For rearrangements, do they have to happen on an adjacent carbon or?
Yes. Yes, it's always going to be the adjacent carbon. You had a question as well? What was that? Why you would have the hydride shift? So here, if you were to shift a methyl group instead of a hydride, you'd end up with another secondary carbocation. So that's not going to improve the stability. But if you shift the hydrogen over, you end up with a tertiary carbocation. So you shift the group that gives you the most stable carbocation if you do a shift. Okay? And that shift will only happen if you can generate a more stable carbocation. All right, let's talk about stereochemistry now. So I'm going to draw another alkene perpendicular to the plane of the board. Okay. We'll react this alkene with HCl. We're going to protonate it. That's going to give us carbocation. I'm going to go ahead and draw our empty orbital, our positive charge. So that carbocation is perpendicular to the plane of the chalkboard. And then that's going to react with chloride. Is there going to be any difference in the rate of the chloride attacking this carbocation from the top face versus the bottom face? No, I see people shaking their heads. There won't. It's going to be the same from the top or the bottom. So it's going to attack at equal rates. I'll just go ahead and use dashed arrows showing both pathways. If we attack from the top, we're going to get the chloride I draw here. If we attack from the bottom, we would get this chloride. Okay. What's the relationship between these compounds? Are they mirror images of each other? They are mirror images. Are they superimposable? They're not going to be. So these are enantiomers of each other. Okay. And we'll form them in a 1-to-1 ratio because we said there's no difference in the rate of attacking from the top or the bottom. Okay. And this fits what we learned previously. The alkene is achiral. The HCl is achiral. We're making a chiral product. And whenever you make a chiral product from achiral reactants, it needs to be formed in a racemic mixture. Okay, so this is going to be racemic because we have a 1-to-1 mixture of enantiomers. Okay. Let's look at a more complicated stereochemical example. So we're going to react this tetrasubstituted alkene with HCl. And I'll draw the products. So how many total stereoisomers can we produce in this reaction? How many stereocenters are we forming? How many stereocenters in this product? 2. So 2 to the n tells us 4 possible stereoisomers. Okay. This figure here, which sadly they took out of your textbook. This was in the older editions of the textbook, and for some reason they took it out of yours, of the 5th edition. But please take a look at this figure. It's available on Learning Suite. It's an important figure. It shows us what's happening in this reaction and how all 4 of these stereoisomers get formed. So we protonate our alkene. There's going to be no difference in protonating from the top versus the bottom. So we're going to get a 1-to-1 mixture of these carbocations. These are chiral carbocations. Of course, the positively charged carbon is not a stereocenter, but the carbon that got protonated is now a stereocenter in this case. Okay. So now chloride can attack from the top or the bottom on this carbocation, giving these two products. It can attack from the top or the bottom on this carbocation, giving these two products. So that's how all four products form. Now let's take a look at this. Let's look at this carbocation that I'm pointing to here. Is the rate of the attack from the top going to be the same as from the bottom, or will there be a difference? There is a difference. Which face will get attacked faster? The bottom. The top is hindered by the methyl group. The bottom just has a hydrogen. So will A and B be formed in equal quantities, or will there be a major product? Yeah, we're going to have A as the major and B as the minor, because that chloride is going to come from the bottom. The same argument applies over here. We're going to attack the chloride's going to attack from the top faster than the bottom. And so D is going to be major over C. Question? Yes, but the transition state is going to look more like the carbocation than the product. So it's the steric hindrance in the carbocation that matters. Okay? Yeah, so we could say, all right, if we have this cis to the chlorine, that's going to be, okay, I see what you're saying, but there's complicated, you have multiple methyl groups and one chloride, so analyzing it in that way is a little more complicated. What we'll focus on is that the chloride is going to approach the positively charged carbon from the less hindered face faster. Okay, so that tells us, so A is going to equal D because those are the two major products. We formed a one-to-one mixture of these enantiomers, and so the major products from those two enantiomers are going to be formed in equal concentrations. And that's good because those are enantiomers of each other. We know they're supposed to be formed in a one-to-one mixture because we have achiral reactants. Similarly, we can say that the concentrations of B and C will be identical to each other. The two minor products will be formed in the same concentration. But we know that A and D are going to be major over B and C. So the concentration of A and D is going to be greater than the concentration of B and C. So we have a major diastereomer and a minor diastereomer, and each of those diastereomers is formed as a racemic mixture. Any questions about that? So the last thing for today is the mechanism of hydrohalogenation, a syn addition, an anti-addition, or both? Both. So the groups can add either from the same face. We see that in A and D in this case, the hydrogen and the chloride are adding from the same face, or they can add from opposite faces. So because hydrohalogenation is a stepwise process, we see a mixture of syn and anti-addition. All right, we'll stop there. We'll pick up with our next addition reaction on Friday.